Hi. Okay, thank you. Okay, thanks for the opportunity to talk here. Okay, I will talk today about Leray numbers of tolerance complexes. This is based on work done with Minki Kim. Okay, so let's begin with a short introduction to simplicial complexes and Leray numbers and some related properties. Okay, so we have V, a finite set, a set of vertices. A simplicial complex is a family of subsets of V that satisfies the following property. For any set A in the family, all of its proper subsets also belong to K. Okay, the sets in the family are called the simplices of K, or faces. The dimension of a simplex is its size minus 1, and the dimension of the complex is the maximal dimension of the simplex. Okay, so we have this abstract definition of simplicial complex, but we can also think of them as geometric objects, as geometric shapes made by gluing together simplices corresponding to the sets in the family. And therefore, we can also study the topology of such a complex. In particular, we can study the homology groups of K. So we denote by HIK the I-dimensional reduced homology group of K with the coefficients in the real numbers. Okay, so informally, the I-dimensional homology group counts how many I-dimensional holes there are in the complex. Okay, for example, if K is this one-dimensional complex, this graph, then it has homology in dimension 1, corresponding to this one-dimensional hole, this cycle. If K is this two-dimensional sphere, it has homology in dimension 2, where the two-dimensional hole is this void enclosed by the sphere. In general, if K is a d-dimensional sphere, then it has homology in dimension d. And for most of the talk, this is the only fact about homology that we will need. Okay. Now, given a simplicial complex K and a set of vertices U, we define the subcomplex of K induced by U to be the complex with vertices U, whose simplices are just the simplices in K that are contained in U. For example, if K is this complex here, and we choose U to be this set of 4 vertices, then the induced subcomplex KU is just this smaller complex. And K is called D-Leray if K itself and all of its induced subcomplexes have trivial homology in all dimensions greater or equal than D. Okay, and we denote the Leray number of K is the minimal D such that K is D-Leray. So, okay, we can think of this Leray number as some kind of homological dimension of the complex, meaning that perhaps we have a complex that has a very large dimension, but if the Leray number is bounded, then in terms of homology, then nothing interesting happens above this dimension D. Okay. A second property, related property that we will use today is the property of collapsibility. Again, we have a complex K, and assume that we have a simplex sigma of size at most D. that is contained in a unique maximal phase of the complex. Okay, for example, here we have sigma, a vertex, it's contained in the unique maximal phase, this triangle tau. Then an elementary decollapse is the operation of removing from the complex sigma, removing sigma and all of the simplices containing it. So in this case, we remove sigma, we remove tau, and also remove these two edges containing sigma. And the complex is called decollapsible if there is a sequence of elementary decollapses reducing K to the void complex. So meaning we can remove all the faces of K by performing such a sequence of decollapses. Okay, for example, if K is this complex here, so okay, it's we can show that K is not one collapsible, and the reason is that there are no possible elementary one collapses to perform because any simplex of size 1, any vertex, is containing more than one maximal phase. Okay, but it turns out that this complex is too collapsible. And for example, we can perform the following collapsing sequence. We can choose sigma 1 to this edge. It's contained in a unique maximal phase, so we can remove them. Now we choose sigma 2 to be a vertex. Okay, it's of size 1, smaller than 2, it's okay. Okay, and so on. Now we can choose sigma 4 to be one of these edges. It is a maximal phase by itself, but it is okay, this is allowed, so you can remove it, and so on. Okay, so we were able to reduce, to remove all of the simplices, so K is too collapsible. Okay, and the collapsibility of a complex K is the minimal D such that it is decollapsible. Okay. And the last property of simplicial complexes that we will talk about today is the property of representability. And it is defined as follows. So assume we have a family of sets F, okay, with sets F1 up to Fn. We define the nerve of F to be the simplicial complex whose vertices correspond to the sets in the family and whose simplices correspond to subfamilies with non-empty intersection. For example, if F is this family of 4 sets, then the nerve will look like this. So we have a vertex for each set, and we have a simplex whenever we have intersection. So here we have a purple, red, green triangle corresponding to the fact that these 3 sets have a point in common. Okay, and a complex K is called D-representable if it is the nerve of some family of convex sets in Rd. So, for example, this complex here is 2 representable. Okay. Okay, so these 3 notions of D-representability, decollapsibility, and D-Lerayness were studied by Wegener in the 70s. So he showed that any D-representable complex is decollapsible. This is known as Wegener's theorem, and he also showed that any decollapsible complex is D-Leray. Okay, so so these are 2 different notions that generalize this this concept of being D-representable. And in fact, many properties of D-representable complexes, or equivalently many properties of families of convex sets in Rd, they extend to this more general families of decollapsible and Leray complexes. And okay, many times it's even easier to understand these problems when looking at this more general set.
Just a small question. I guess all of these inclusions are strict, right? Meaning there are Leray complexes that are not decollapsible.
Yes, right.
Okay,
They are strict except in special cases for one collapsible, it's the same as one Leray, but I think this.
Okay, I see.
Strict.
All right, thanks.
Thank you. Okay, so one such property of convex sets that generalizes nicely to this more general setting that we will talk about is Helly's theorem, which says the following. So we have a family of convex sets in Rd, C1 up to Cm, and assume that any d plus one of these sets have a point in common. Then there must be a point in common to all of the sets, to all of the Ci. Okay, for example, in dimension 1, so convex sets are just intervals, and Helly's theorem tells us that if we have a family of intervals and any two of them intersect, then in fact there must be a point in common to all of the intervals. And here we have an example in dimension 2 where we have 4 sets, any 3 of them intersect. But you can check that there is no point in common to all of the sets. So Helly's theorem doesn't hold here. Well, and of course, the reason it doesn't hold is that not all of these sets are convex. Okay. Okay, so I want to show you how this. So in order to extend this result to this decollapsibility and delirayness, we need to first translate it in terms of simplicial complexes. In order to do that, we need to talk about missing faces of a complex. So a missing face of a complex is a set of vertices tau that satisfies the following two properties. It is not a simplex in the complex K, but any proper subset of tau is a simplex. For example, if K is this complex here, then we have two missing faces. We have this missing triangle. It's not in K, but all of its proper subsets, all of its edges belong to K. And we have this missing edge. Again, it's not in the complex, but its subsets, its vertices belong to K. And we denote by h of K the maximum dimension of a missing face. So for example, for this complex here, we have hk equals. Okay, now in terms of missing faces, Helly's theorem says the following. If K is d-representable, if it's the NERD of a family of convex sets in Rd, then h of K is at most d. Okay, the missing faces of this complex are of dimension at most d. Okay, and it turns out that we don't have to assume that K is d-representable. It's enough to we can replace this condition, but by the weaker properties of being decollapsible or even being Leray. Okay, so if K is Leray, then the same property holds. The missing faces are of dimension must be. Okay, so the work I want to show you today is related to a different version of Helly's theorem called the tolerant Helly's theorem. So in order to to present you that result, I need to talk to you first about the following problem by Erdős-Gallai. Okay, so we have H, a family of finite sets, or just an hypergraph. A set of vertices C is a cover of H if it intersects all the sets in the family. Okay, and the covering number denoted by tau of H is the minimum size of the cover. For example, if H is this family of 5 sets, we can choose C to be these 2 points. So this is a cover of size 2. It's easy to check that we don't have covers of size 1. Therefore, tau of H is, in this case, 2. And Erdős and Gallai asked the following question about the covering numbers. They wanted to find, given integers r and t, they wanted to find the minimum m such that the following property holds. For any family H of sets, each one of them of size at most r, if any subfamily of H consisting of at most m vertices has covering number at most t minus 1, then H itself also has covering number at most t minus 1. Okay, so you can see this is some kind of Helly-type result. If this property holds for all subfamilies with certain condition, then it holds for the family itself. Okay, so it is not clear that such an M exists at all, but okay, but this was proved by Erdős and Gallai, and they also found out the exact value of this number eta RT in some special cases. So they showed that for r equals 2, then eta 2t is 2 times t. So this is the case of graphs, families of size or of sets of size 2. And in the special case t equals 2, they show that eta r2 is r plus 2 over 2 squared. For general r and t, the best bound is due to Tusa. We show that eta rt is bounded by this sum of binomial coefficients. Okay, and this bound is tied up to a very small constant. So this is really the right bound. So in terms of asymptotics, this if you fix t and let r grow, then this number behaves like r to the power of t. And if you fix r and let t grow, then it behaves like t to the power of r minus 1. Okay, so these are the Erdős-Gallai numbers. We will see in a moment how they are related to the tolerant version of Helly's theorem. Okay, so we have let F be a family of sets. We say that F has a point in common with tolerance T if there is a subfamily of F prime, of size at least the size of F minus T, such that okay, this family has non-empty intersection. Or in other words, F has a point in common with tolerance T if, after removing at most T sets from the family, we are left with a family that has a point in common. Okay, for example, we can look at this family of sets here. So it is clearly has empty intersection, but we can choose 2 of these sets and remove them. And the remaining family has non-empty intersection. Okay, so here we say that F has a point in common with tolerance 2. Okay, and the tolerant version of Helly's theorem is a result by Montejano and Oliveros, and it says the following: if F is a finite family of convex sets in Rd, and any subfamily of F of size eta d plus 1 t plus 1 has a point in common with tolerance T, then F itself must have a point in common with tolerance T. Okay. Okay, well, this number eta d plus 1 t plus 1 is exactly the corresponding Erdős-Gallai number that we talked about before. Okay, so now I want to translate this result to the language of simplicial complexes, just like we did with Helly's theorem. In order to do that, we need to introduce the notion of the tolerance complexes. So again, K is a simplicial complex, and we choose T an integer. The T tolerance complex of K is the following simplicial complex. It is denoted by TTK. The vertices of the T tolerance complex are just the vertices of the original complex V, and the simplices are the sets of vertices sigma that contain some subset sigma prime of size at least the size of sigma minus T, such that sigma prime is a simplex in K. Or in other words, sigma belongs to the T tolerance complex if, after removing at most T vertices from sigma, we are left with a simplex in K. Okay, for example, if K is this complex here, then the one tolerance complex looks like this. So, so all of the edges belong to the one tolerance complex, because any edge we can remove one of its vertices, then the remaining vertex is a simplex in K. And we also have these two triangles. So any of these triangles, we can remove its top vertex, and then we are left with this edge that belongs to the original complex K. Okay, so you can see the similarity of this definition to the definition of points in common with tolerance. And indeed, if F is a family of sets, then the T tolerance complex of the nerve of F is the complex whose simplices are exactly the subfamilies of F that have a point in common with tolerance T. Okay, now using this, we can rephrase the tolerant Helly's theorem in terms of simplicial complexes. Okay, and so if K is D-representable, then the missing faces of the T tolerance complex of K are of dimension at most this number, eta d plus 1, t plus 1 minus 1. And in fact, Montejano and Oliveros, they proved something stronger than this. They show that we don't need to assume that K is D-representable. It is enough to assume the much weaker property that the missing faces of K are of dimension at most D. Okay, so this was the starting point of our work. We looked at this theorem and we wanted to know, okay, so we really need to assume very little about K to obtain this conclusion. So what happens if we know more about K? For example, what happens if we assume that K is decollapsible or Leray? Maybe you can say something more about the T tolerance complex. And so we made the following conjectures. So if K is the Leray, then the T-tolerance complex is this number eta minus 1 Leray. And if K is decollapsible, then the T-tolerance complex is H minus 1, eta minus 1 collapsible. Okay, so these are still conjectures, but we were able to prove some results related to this. Before I talk about the results, I want to show you some examples showing that at least in some special cases, these bounds eta d plus 1, t plus 1 minus 1 are the best that we can hope for. Okay, so the first example is the following. We take a family of sets C consisting of t plus 1 copies of each facet of a d-dimensional simplex. So for example, in dimension 2, we take t plus 1 copies of each of the edges of a triangle. So the nerve of this family is by definition d-representable, and in particular it's decollapsible in Leray. And we want to know what is the T-tolerance complex of this nerve. So I remind you the T-tolerance complex, its simplices are the subfamilies that have a point in common with tolerance T. So you can see that C itself, it doesn't have a point in common with tolerance T, because any T sets that you remove, you are still left with at least one copy from each of these edges, and then we have empty intersection. But it is enough to remove any of these sets, and now the remaining family has a point in common with tolerance T, because we can remove the remaining T copies of this edge, and the rest of the sets have a point in common. So this shows, in fact, that the T-tolerance complex of this nerve is the boundary of the simplex on okay, d plus 1 times t plus 1 vertices, the number of sets in the family. So in particular, this is a d plus 1 times t plus 1 minus 2 dimensional sphere. Okay, so it has homology in this dimension. Therefore, it is not okay, d plus 1, t plus 1 minus 2 Leray. Okay, in the special case d equals 1, this number is just 2 times t, and this is exactly eta 2t plus 1 minus 2. Okay, so this is one less than the bound in the conjecture. So at least for this special case d equals 1, this bound eta minus 1 is really the right one. Another special case where we have external examples is the case t equals 1. And so this is an example by Montejano and Oliveros. They show that there are families C of convex sets in Rd such that the one tolerance complex of their nerve is not d plus 3 over 2 squared minus 2 Leray. Okay, and this number is exactly eta d plus 1 t plus 1 minus 2. Okay, so this is exactly one less than the bound in the conjecture. Okay, so at least in these two special cases, this eta d plus 1 t plus 1 minus 1 seems to be the right goal. Okay. Okay, so now I will show you what we did manage to prove. So first we define a number HTD in the following way. For t equals 0, then this is D, and for t larger than 0, then it's defined by this recursive formula. The details are not very important. And we proved the following. If K is a D-collapsible complex, then the T-tolerant complex of K is HTD Leray. Okay, so this result is weaker than our conjectures in two different ways. First, note that we are assuming here that K is decollapsible, the stronger property, and we obtain a bound on the Leray number of the T-tolerance complex, which is the weaker property. And also this bound HTD is, in general, it is larger than the bound, the conjectural bound is Erdős-Gallai number. Okay, but in some special cases, the bound we obtain here is not too bad. For example, for D equals 1, we obtain a bound 2t plus 1, which is, in this case, it's exactly the bound in the conjecture. So this is really the optimal bound. In the special case, t equals 1, we obtain a bound of d squared plus 2d, which is about 4 times larger than the bound in the conjecture, which is okay, also not too bad. In general, if we fix t and let the d grow, then HTD behaves like d to the power of t plus 1, which is the right order of magnitude. Okay. So as I just told you, in the special case t equals 1, we prove that if K is decollapsible, then the one tolerance complex is d squared plus 2d Leray. And what we were hoping to prove is that the improved bound d plus 3 over 2 squared minus 1. So okay, we know this is true for d equals 1, and in addition, we were able to prove this also in the special case d equals 2. So we show that if K is 2 collapsible, then the one tolerance complex of K is 5 Leray. Okay, where 5 is exactly the number we obtain by setting d equals 2 here. Okay. Okay, so these are results. In the time we have left, I will show you some ideas from the proof, or a very short sketch of the proof. So we will need some definitions. So again, K is a simplicial complex on vertex set V, and let sigma be a simplex in K. We define the link of sigma in K to be the subcomplex of K, consisting of all the simplices of K that are disjoint from sigma and whose union with sigma belong to K. And we define the costar of sigma in K to be another subcomplex of K consisting of all of the simplices that don't contain sigma. Okay, so the costar of sigma is obtained from K by removing sigma and all of the simplices containing sigma. Okay. Now we have an equivalent definition of decollapsibility due to Tanzer. He showed that K is decollapsible if and only if either the dimension of K is smaller than D, or there is some simplex sigma of size D that is contained in the unique maximal phase tau, okay, different than sigma, such that the costar of sigma in K is decollapsible. Okay, so we obtain just recursive definition for decollapsibility. Okay, and this definition, it shouldn't this result shouldn't surprise you so much. Okay, this is quite similar to the original definition. We have a simplex of size D containing a unique maximal phase, and the costar of this simplex, right? It consists of all the simplices that don't contain sigma. So this is exactly what we obtain after performing the elementary decollapse, removing sigma. So, so saying that the costar is decollapsible is the same as saying that after we perform the first elementary decollapse, we can continue performing decollapses until we remove all of the simplices. Okay. So, so we can begin the proof now. So, we have K, a decollapsible complex. We want to show that the T tolerance complex has bounded Leray number. So by Tanzer's theorem, we have two options. The first case is that the dimension of K is smaller than D. And in this case, then the dimension of the T tolerance complex of K, it's easy to check that this construction, this T tolerance construction, it can increase the dimension by at most T. Okay, so the dimension of the T tolerance complex is at most smaller than D plus T, which is smaller than this HTD or bound. And of course, if the dimension of the complex is bounded, then also the Leray number is bounded, because we don't have homology in a dimension where we don't even have simplices. Okay, so in this case we are bound. And the second possibility is that we have a simplex sigma of size D contained in a unique maximal phase tau, such that the costar of sigma is decollapsible. And in this case, okay, so just a reminder, we want to show that the homology groups of this T tolerance complex are 0 in dimensions larger than this number HTD. We actually have to show this for this complex and also for its induced subcomplexes. But it turns out that the same argument holds for K and for its induced subcomplexes. So it's enough in this case to show this. And what we do, we will look at the subcomplex of the T tolerance complex, okay, which is the T tolerance complex of the costar of sigma in K. Okay, so the costar of sigma is a subcomplex of K, so its T tolerance complex is a subcomplex of the T tolerance complex of K. And we look at the long exact sequence of this pair of complexes. Okay, so we have this sequence relating the homology of the T tolerance complex of K and the T tolerance complex of the costar, and this relative homology between these two complexes. Now, the costar of sigma, by assumption, it is decollapsible, and it is also smaller than the original complex K. Therefore, we can argue by induction, and we can assume that these homology groups are 0 for k larger than this HTD. Therefore, in order to show that this is 0, it is enough to prove that the relative homology is 0 for k larger than this number. Okay, and in order to do that, we need to understand how this relative homology group looks. And we prove the following formula. So we show that this relative homology is isomorphic to this. Okay, it looks a little scary, but okay, we can try to understand this. So we have a direct sum of homology groups of the union of the tolerance complexes of some links of the original complex. Okay, but okay, K is decollapsible, and it is known that links of decollapsible complexes are also decollapsible. Okay, this is a result of Chmielnicki. And okay, so this is decollapsible, and we are looking at tolerance complexes of a decollapsible complex. Again, by induction, we can apply induction on this T or even on the size of the complex, I think. And so again, by arguing by induction, we can assume that this complex is H T minus sigma prime D Leray. So it has bounded Leray number. And now we have a union of such complexes with bounded Leray number. And then we can use a result of Gallai and Meshulam that says that the union of complexes with bounded Leray number has also bounded Leray number, which is bounded by more or less by the sum of the Leray numbers of the complexes with some small correction. Okay, so this complex, we have a bound in the Leray number. If you recall, we defined this number HTD exactly in such a recursive way. So this sum here turns out to be exactly HTD minus D minus 1. Okay, so we have here the K minus D minus 1 dimensional homology groups of an HTD minus D minus 1 Leray complex. So if K is larger than HTD, this is 0, which is what we wanted to prove. Okay, so this shows, this finishes the proof. Okay. Okay, and in the minute I have left, I want to show you a very simple geometric application of our results. So let C1 up to C6 be families of convex sets in the plane, and assume that any colorful subfamily, so any family consisting of one set from each of these families, if any such subfamily has a point in common with tolerance 1, then there must be some I such that Ci also has a point in common with tolerance 1. Okay, so this is a kind of colorful tolerant Helly theory. Okay, and this this result follows by just immediately by applying another result of Gallai and Meshulam called the topological colorful Helly's theorem, which says that if we have a complex with a bounded Leray number, then it satisfies some version of the colorful Helly theorem. Okay, so this is what I wanted to show you today. Thank you for listening.
All right, thank you very much for that talk. Are there any questions?
So I don't know whether you know this technique of shifting, of algebraic shifting. Is it somehow? Have you ever looked into that?
No, I didn't try it.
But you can probably ask Eran about it if you're.
Yes.
Or we can talk about it at some point. I was wondering how this relates to. I mean, the collapsibility, I guess. I mean, I don't know how it relates to the tolerance complexes. Actually, what it does to them. Roy, do you know?
Karim, what techniques do you talk about?
Yeah, I wanted to just know what happens if I apply algebraic shifting.
Ah, I see. No, I don't. Well, my guess is that it does preserve collapsibility.
Well, actually, it induces it, right? I mean, the shifting makes things collapsible. So the question is more what it does to the tolerance complexes and the Leray property. So the question, I mean, usually somehow the shifting is kind of algorithmically simpler, right? If it turns a Macaulay complex into a Scherlable complex, for instance.
Right.
So I mean, the question is more how the other properties relate, and then maybe you can prove some things that you now prove under the decollapsible assumption more general.
I see. Yeah.
Yeah. Anyway, we can talk about it, Alan, at some point.
Okay, sure.
Okay, any other questions or new proof ideas or approaches? That doesn't seem to be the case. So thank you again, Alan. I will